Okay guys, welcome back to this physics tutorials. My name is Samuel D. Koidia, and for your physics lesson today, we're going to look at the principles of moment, and I'm going to explain a couple of principles that are attached to this, and we see the application in life, and we see our approach as we go. We will look at the principles of moment, and first of all, what's the moment? The moment is the turning effect of a force. It explains why the hinge of doors are not closed. The handle of doors are not very close to the hinge. You know that there's a point on the door where you push the handle to open, but the handle is always far away from the hinge. You know the hinge of a door, and you have the handle far away somewhere there. So you see that there is a distance between them. Why is that so? Why are the handles of doors are not close to the hinge? Because we want to maximize the moment. That is the turning effect of that force. So moment is actually the turning effect of a force. And we said that it could be, we can represent it mathematically as the product of it is the force times the perpendicular distance. Is the force times the perpendicular distance now. And we want to look at the principles behind the moment. Actually, we look at principles of moment, or conditions for equilibrium from a system of coplanar forces. And what is that moment? We can call it the principles of moment, or we will look at it as the conditions for equilibrium from a system of coplanar forces. And what is that? The first condition for an object to be in vertical equilibrium, it means that the upward forces must balance with the downward forces. If that's not possible, then that object will not maintain vertical equilibrium. So if for you to maintain vertical equilibrium, you have to ensure that the upward forces must be equal to the downward forces acting on the object within that plane. And now again, if you want to look at the second part of that principles of moment, that's the conditions for equilibrium for a system of coplanar forces, we can also look at it horizontally. If you want to maintain horizontal equilibrium, I must ensure that the clockwise turning moment must be equal to the anti-clockwise turning moment about a point called a pivot. So what we're trying to establish is that we have to explain how the principles affect the turning effect of objects. So we want to look at a common material we find in our labs, like the meter rule. So our investigation, we want to assume as a scientific investigator, we want to investigate the center of mass of a meter roll, and we want to look at a couple of materials which I've put together so that we can go through this. So let me first of all go through the materials there. I have a meter roll here. That's the meter roll there. That's the meter roll in that diagram. Now I have a weighing balance here. I have a weighing balance somewhere there. I'm going to use it for something very soon. You see that. I have a wooden pivot somewhere here. I have this wooden pivot. It's a nice one like this. It's a wooden pivot. Now it's also called a knife edge, as a matter of fact. So we have that. And I have a couple of slotted masses. I have 10 gram masses here, and they are on this mass hanger. I have 10 grams, 10 gram, 10 gram. So like this is 30 gram together with a hanger. I have a couple of 20 gram masses, also slotted masses. I have 20 gram, 20 gram, 20 gram, 20 gram together with a hanger. So I have 80 gram here and I have a couple of loops that I have made here to help me suspend those masses on this meter roll. I have a couple of loops. You can see that I have minimized my error so much that the loops are not too long, so that they can reduce my error. And now this is a loop. I have made a loop with a string somewhere there, and I have a scissors which I use to just cut the loops into that order. So the first thing I want to do is to look at first the center of mass of this. Or first of all, I want to find out the mass of this meter roll. I want to use this balance, this weight balance, to find the mass of this roll. It's possible that I can find it once and just write it at the back or the reverse side of this meter roll. So I want to look at the balance, and I'm find the mass of this. We know that the mass of an object is the quantity of matter it possesses. So we want to say what quantity of matter exists in here. I want to find that mass by using my balance here. So I look at it. I want to put on the balance first. So you can see that it is, now it is 0. I have ensured that it is 0 gram. I have not placed anything right there. It's 0 gram. So 0.0 gram if you like. Now I want to put this, now I can put this meter rule here and approximate the, try to get the mass of this in gram is 105.8. Yeah, the quantity of matter contained in this one, it may vary from rule to rule, but now I have 105.8 gram here. So this is, I'll just record that. Let me call it the mass of the roll. This is 105.8. Yep, so now that is the mass of the roll. Now I'll record it. So now this balance helps me to actually find the mass of this. If I do want to use this balance again, I can write the masses at the reverse side of the meter roll, so that it can help me to recall very fast. So I don't need to put it there again to measure. I can just look at the reverse side of the meter roll, then I can find the mass there. But I'm not going to write it there now because I have to use this meter roll for some other thing. So what I can write, I have measured the mass of this meter roll. So I can keep my balance somewhere there. Now I can now proceed with the experiment. The first instance, I want to find the center of mass. First of all, what's the center of mass of this? We said that it is where the resultant weight acts on an object. It is where the resultant weight acts on the object. And where this mass is concentrated, I want to discover that point first of all. And it's a meter roll. So where it is going to balance horizontally will give me where the resultant weight acts, which is the center of mass of this meter roll. It will vary from meter roll to meter roll. So how am I going to find the center of mass of this meter roll? I have to ensure that I use my pivot and try as much to find a balance point. It may vary from person to person. So you have this. I have to ensure that I place it carefully so that I have a horizontal, it's balanced horizontally. You take it, you just have to be patient with it. So this is at 50, the 50 centimeter mark. This is a meter roll. It is uniform. It's 100 centimeter. Now I got it at 50, so exactly at 50 centimeter. That's the center of mass. That's where the resultant weight acts on this object. So now we want to ensure that if I want to find the mass of this meter roll, which is what I want to investigate, I want to find the center of mass of that meter roll, I have first of all located it. That point where the meter roll balance horizontally, I have labeled it as G. That is the center of mass of that meter roll. So it is where the weight balances, the meter roll balances horizontally. So I have marked it for this meter roll. It may differ from meter roll to meter roll. Some of the meter rolls you have like 50.1, some is 49 point something. So it's just within the middle of that roll. That's why you call it a meter roll. A meter roll is uniform, 100 centimeter. So if you are around 50, you are around 51, you are around 49 point something, don't get panic with that. It is just around that, so you're still within the range. So now let's look at it is now at 50 centimeter. That is where the resultant weight acts. That's the center of mass of this meter roll. Now I want to find the center of mass by verifying. I want to now use a couple of a couple of masses. I'm going to take, let's say, 80. I'm first of all going to check. This one is, I just did it on the balance there. I just measured it and it gave me that. Because of experimental errors, I will not have exactly what I got from that balance, but I'll get something closer to that. So let's see how we can investigate the mass of this roller using these principles of movement. So now I am I'm going to just use one of these, or let me use all of them in that case, because I just want to do it once and for all. Then later I can come to vary. I'm doing two experiments all together here. First, I want to investigate first the mass of this roller. I want to find this M on this roller. But first, I have identified where the center of mass is, which is that G. That is where it has balanced. So that my point is already G. So I call it, let me label it at 50 in that case. So the point G is at 50 centimeter. Okay, so now I've got that center of mass. Now at the center of mass, that is where the resultant weight acts, or the resultant mass of this guy. And this is what we want to investigate. We want to find the mass of this roll. I'm just going to do a snap experiment just to verify that. Then later on we'll come to the experiment proper. So I've taken a couple of slotted masses here. Let's say this is 20, this is 20, this is 20, and this with the hanger together is also 20. So I have 80 gram here. This is an 80 gram mass. Now I'm going to find a loop, let's say a very short one for that matter. I'm going to hang it somewhere there so that I can suspend it on this roll. And now I already have my center of mass at 50. Remember that, that's 50. Now I'm coming to hang this at a variable position. This, I already know the mass, so this the mass that is hanging, let me call it, this mass that is hanging, I want to call it 80 gram. Because I've just placed in 20, 20, 20, 20 times 4 to get out the hanger, it's all 80 grams. So that 80 gram with this loop. Now I've got this mass here, and I've got this mass here. But remember the concept here. Before I proceed, I first of all want to look at the principles of movement. The first, we said, for vertical equilibrium to be maintained, the upward forces must balance downward forces. That's what we said. For vertical equilibrium to be maintained, the sum of upward forces must balance sum of downward forces. There. So the sum of upward forces must balance the sum of downward forces. That is the component of the principles of movement. That is one condition for equilibrium, for a system of coplanar forces. These are coplanar forces acting in the same plane. Co means the same plane, so it's coplanar forces. So for the object to maintain vertical equilibrium, it has to ensure that the upward forces must balance with downward forces. What about horizontal equilibrium? If I want to maintain horizontal equilibrium, like for instance, like that, this is a force acting there, and there is a distance here, let's call it F1, and I have another force acting here. This is that, and that is a distance x2, and this is the pivot. That's a turning point. Well, second condition for equilibrium, I'm also ensure that if I want to maintain a horizontal equilibrium, I'm also ensure that the clockwise turning moment must be equal to anti-clockwise turning moment about that point called the pivot. So I must find the moment. And remember the formula for moment, we say moment is force times perpendicular distance. So for this object to maintain horizontal equilibrium like this roll, it must balance the clockwise turning moment. This is clockwise turning moment. So what do I mean by clockwise turning moment? If I tend to turn this, that is the turning effect. If I tend to turn this material, you're going to find out that the meter roll will go the other way, this way, because this force is acting that way. So it means it is moving within the clock direction, so we call it clockwise turning moment. So that is the force times the perpendicular distance that gives the clockwise turning moment. Now, if I want to also maintain the horizontal equilibrium according to my principle, it says that this clockwise turning moment must be equal to the anti-clockwise turning moment. This other force is moving this way. So this is, if I turn it this way, if I move it this way, it's going to be anti-clockwise or anti-clockwise. So the clockwise turning moment must be equal to anti-clockwise turning moment about that point called the pivot. So now I want to state that this is clockwise, this is anti-clockwise. So for this meter roll or any other object that is trying to maintain equilibrium horizontally, it must ensure that the clockwise turning moment must be equal to anti-clockwise turning moment about that point called the pivot. So if I now do the math, I have already defined movement as what? The first times the perpendicular distance, and you must know that it's perpendicular because this is going this way, and this is the force that's perpendicular. So there's a perpendicular distance here. This one too is also perpendicular. So it's force times perpendicular distance, force times perpendicular distance. So now what's the force? The clockwise force is this F1 and X1. So it is F1 times X1 is equals to, this other one is F2 times X2. So for this moment for this object to maintain equilibrium horizontally, I must have the following. This is F2, X2. This is the basic equation. So this force multiplied by the distance, that is force times perpendicular distance from the pivot, the point of the pivot, must be equal to the force times perpendicular distance on the other side, that's anti-clockwise. So this principle is called the horizontal conditions for an object to maintain horizontal equilibrium. Remember, the principle is actually 2-in-1. We have principles of moment or conditions for equilibrium for a system of coplanar forces. The upward forces must balance with downward forces for vertical equilibrium to be maintained, and for horizontal equilibrium to be maintained, the clockwise turning moment must be equal to anti-clockwise turning moment about a point called the pivot. And that is exactly what we have to experiment here. So let me look at my diagram again. So I come back here. This is the pivot. Now this is the mass. This mass is 80 grams. So I'm trying to find, I'm going to adjust this string, this loop along. That's why the loop is now made a little bit hollow and big and it's free a lot, so that I'll be able to adjust it on this meter rule. Now I'm coming to, so remember this position. This position was the center of mass of that stuff. We have just located the point where the resultant weight acted there. But that weight is the component of its mass. So we're going to find the mass at that point. For as much as we can identify here, then we can find the mass of this rule, which is what we want to do. So that's the pivot. So I'm now using the 80 gram mass to just prove that by principles of moment, I can find the center of mass of this rule by principles of moment. I've just verified the mass using the digital balance. So I want to now adjust this thing and just put it right here. This is the, now I'm going to ensure, one of the precautions that you can do is to ensure that the mass is not on the table. So I'm going to move this a little bit so that it can freely hang in, so it can hang freely. So now when I hang it freely like this, I've now moved it from the edge of the table. So let me just put it here so that you can see something. So I'll put it right here. This is it was at 50 when I place it, but as you can see, if I put a mass there, I cannot maintain equilibrium again at that 50. It's not possible. So I have to ensure that I adjust this, but bearing in mind the center of mass, which is the 50 gram, I know that already, and that is where the mass is going to act. The mass of this rule will act, because that's where the resultant will act. So now I have placed this rule. I can place this at a point which I can. Yeah, let me just put it at the point 15 centimeter. So 15 centimeter from here. This is 15 centimeter. I just place it there. I want to keep this constant as possible. I can keep this constant, but I can come and vary the position of the balance point where this rule is supposed to balance. It's not going to balance at 50 anymore because I have placed a weight there. But the weight of this rule is now going to balance in horizontal equilibrium with these masses. So I've placed these masses at 15 centimeter. Now I'm going to adjust this. It cannot be at 50 anymore because there is a weight over there. So if I want this rule to balance horizontally, I have to ensure that the clockwise turning moment here must be equal to anti-clockwise turning moment above this pivot. So I'm coming to adjust the position on the pivot. So it can't be on that 50 anymore. So I'm going to now adjust it such that I have a horizontal balance position from here. So now I'm still adjusting such that I have a balance point so that the rule becomes horizontally balanced. Now it is horizontally balanced with that 80 gram hanging there. And remember, my G was at 50 because this meter rule was assumed to be a uniform meter rule that acted at where the resultant weight at, which was the 50 centimeter mark. Now if I look at this pivot is no more at that 50 centimeter mark. So it means that this clockwise turning moment, that is the force created by that weight multiplied by the distance here, is going to balance with, it's going to be equal to the distance to that 50. This was the point where the rule initially had its center of mass. So I am now looking at this number. This number, the difference between this number and this one, where that was at 50. So I'm looking at the point. The point was at 50. So now this is 35, 36, 37. So now I have 50 somewhere here. This is the point 50 is here. that was the original position, that was the G. So you can see that now this G, that is the weight of this meter roll, is now the mass, which is the constituent of its weight, is going to now balance. So it means there is a force here. That mass of this roll is now balancing the whole weight that is here. So this is the clockwise turning moment. It must be equal to anti-clockwise turning moment. So now the resultant weight of this roll is acting at the 50 here. So this point is no more 50, but that was the 50 here. But there is a distance now between this pivot position, the new pivot position, and this. And that is the point I have tried to put here. So this distance between these pivots now to this mass, this 80 gram, is X there. In that case, I've just labeled it at X. But there's another distance between the pivot here onto the center of mass, where we got initially. When there was no mass on this roll, I took the center of mass initially. That was at 50, because I assumed it to be 50 centimeters, and that was why it balanced. So now we have the 50 around here. So this distance and this distance to here, from here to here, is what is identified by the variable y. And this distance from here to here is what is identified by that X over there. And the 80 gram is what is suspended here. So I've left it there for some time. Now it is in equilibrium. I now know that this has balance in equilibrium. So this guy is at 15, and now the balance point is somewhere around 35 here. So 15 and 35. I just draw something for you here. So you see, I'm trying to draw that picture you have shown there so far. So I have, so the pivot is now at 35. So this is, it is now balanced at 35 centimeters. So I have 35 centimeters somewhere here. That's the pivot. Now I still have my 80 gram mass. That is somewhere there. This is the 80 gram mass, and it is at a point 15 centimeters from the zero here. This 15 centimeters here. So now, on the center of mass of this roll, where the resultant weight acts, which is the mass we are trying to find, the center of mass of this roller, is, it was somewhere around 50 when I started the experiment. So now this is, let's say this place is 50. So I still have my G was somewhere here. This is at 50 centimeters. So now there is a weight here, which is the mass of the roller. So this what I've drawn here so far is what is there. This is the 80 gram mass, which is attached at 15 centimeters, and we have the pivot, which is now balanced at 35 centimeters. Now we have the center of mass, which we found initially because the meter rule was uniform. So we assume it to be, it was around 50 actually, no assumption, we did it. So we have the 50 there. So this is the diagram. This experiment, that's the diagram. So now I want to now use the principles of movement, which says that for this meter rule to be in this horizontal equilibrium, something has taken place here. It is now maintaining horizontal equilibrium because the conditions for systems of parallel forces that are coplanar, for them to maintain horizontal equilibrium, the clockwise turning moment must be equal to anti-clockwise turning moment about this point called pivot. So now this is the moment I'm trying to calculate. That is the force. That is the force generated by this mass is hanging here, multiplied by the distance here. This is the moment, it's clockwise turning moment. It's going to be equal to, it is now equal to the distance from this 35 to this 50, and multiplied by the mass of the roll, which I want to find. That's the center of, or the center of mass of the roll, or the mass of the roll. I found the center of mass. I now want to find the mass of the roll itself to verify. I want to find the mass of the roll by this method. I was able to find the center of mass by measuring it, by finding the center of mass by using the pivot. So now I want to use that same experiment to verify the mass of the roll here. I've already taken the mass of the roll by the balance over there. So now this is 50. Now it is horizontally balanced. It could be like this, and we'll do the calculations. Let's see what happens there. So we say that this is clockwise turning moment, and this is anti-clockwise turning moment. This is anti-clockwise turning moment about that pivot. So I have this 15 to this 35. I already have a 20 centimeter at that space. So we have, this is 15, so to 35 minus 15 will give me 20 here. That's how I got a 20. So I come back here. This is the same. If I have to subtract this 50 from this 35, I'll still have 15 somewhere here. This is 15. So this is the distance 15. So if I come back to my principles over there and I use my principles now, I can now find the mass of this roll which I want to investigate. I want to investigate the mass of the roll. First, I investigated the center of mass of the roll. Now I was able to find that by getting the point where it is horizontally balanced. Now we want to find the mass of the roll. So the mass of the roll can be generated from our calculation. It's the clockwise turning moment. This is 80 times, that's why I call it 60. This is clockwise turning moment must be equal to anti-clockwise turning moment. So it is force times perpendicular distance. So this is 80 times 20. Is equals to, must be equals to anti-clockwise. This is anti-clockwise. This is 15 times m. So I have 15 times m. And how did I get this 15? This is, I subtracted the 50, which was the center of mass, from the 35. So this distance is 15. That's how I got that. That is from the initial G position. So now I have to do the math there. If you have a calculator, you can now walk along with me, and you also use your own calculator to verify this. This is 160. So we have, so I move through. I have the 1600, then we have divide by 15. Divide 15. This gives us 106.7. So you can do the math. You have 1600 divided by 15. I divide here by 15. So this mass, which from my calculator, you can also use your own calculator to get it. So I have 106.6. So let's say 0.7. 106.7. Now I got 106.7, but remember when I did my research first, when we measured it, we recorded it somewhere that it was somewhere around 100, and I think I've cleaned it. This was the rule. So let's still come and verify it from the balance. This is the mass of the rule. Now we have calculated it as 106.7 gram. So now we want to look at we want to verify it from the balance. So the balance, we will not get exactly what is on the balance, but we will go closer to it with that experiment. So we just want to verify this figure here by the weighing balance somewhere here. So I'll remove this here. So I'll come back here. I can put this balance on. It is at 0.0 gram right now. There's nothing on this balance, so I'll put my rule there. Yeah. So if you put the rule here, I have 100, and you can see it is 105.8. So 100 from the digital balance is 105.8. So now if it's approximately almost the same like this, because there are some other factors that are responsible for this. Maybe I do not allow the balance to actually get a horizontal dimension before reading there. I just took a rough estimate, but if I did it real perfect, I was going to get that. But however, we stick closer. Look at that. It's a very good figure. Look at it. The digital balance, the digital answer is 105 gram. 105.8 gram. Now, when we did the experiment, we were able to get 106. So just a small difference there. So that is another way of finding the mass, the rule, the mass of this rule by these principles of movement. So I can verify it from the balance, but I can also verify the mass by using the principles of movement. Remember the principles of movement, we said that it's for an object to maintain horizontal equilibrium, it must obey these rules. What are the rules? For you to maintain vertical equilibrium, first of all, the upward forces must balance downward forces. And that is, by extension, Newton's third law. Because Newton says that to every action there is equal opposite reaction. So that's why you see the television on the table. Because the television is exerting a weight on the table, and conversely, the table also is exerting a normal reaction. So the two forces are equal and opposite, and they cancel each other. That's why the resultant force on the television is zero. That's why the television stays on the table. The same principle goes there. So if you are maintaining vertical equilibrium, the upward forces must balance with downward forces. And you want to maintain horizontal equilibrium, then you must ensure that the clockwise turning moment must be equal to the anti-clockwise turning moment about a point called a pivot. When that is maintained, then you can see that the rule, whatever material that you're trying to put in equilibrium, it will be in horizontal equilibrium. And we need this concept a lot in construction of edifice or construction of structures. You cannot just put a beam and you want to balance that beam, you don't know where the center of mass acts. You need this principle in day-to-day life. So let's proceed a little bit. Now we want to proceed with the same experiments. Now I have a couple of relationship I want to establish here. I want to see what will happen to the distance between the pivot and the balance point if I fix these masses at 15 centimeter, then I now change these masses and see what will happen. I'm going to fix one. I'm going to fix this string at 15 centimeter like I did initially. Now I'll change the masses. I'll begin to increase the masses as I'm moving. Then when I increase the masses, then I will find the balance point. I want to see what's the relationship between this x and the mass that I'm going to be varying. I'm coming to vary the mass. So watch out for this. We have done the first investigation. We wanted to know first the center of mass by the pivot. We've done that. We want to find the mass of the root. We have done that so far. We still want to use this experiment to investigate a couple of variables here. One, we want to look at the relationship between this x here, this distance from the pivot, the balance point, consecutive balance point, and the masses. As the masses are changing, what will happen to this balance point? What will happen to this distance x? And by extension, what will also happen to this y distance? So that's what we want to investigate. So science investigators, I want you to follow up with me. Let's move along with this investigation. We are all journalists, scientific journalists. Let's move with that. So let's go with the first concept. We have already explained that. Now I'm going to look at Now I'm going to move these masses. I'm going to be changing the masses. I want to start up with, remember, I have already got the balance point first. That was the point where the resultant weight acted here. That is still the 50. That was my G initially, it's still there. So the 50, it's still at 50. Just a little. So it's balanced there. Yes, let's assume it's already balanced at 50, so I get there. Yeah, so now it's still at 50. So now what we're trying to do, we want to now vary these masses. I'm still going to fix these masses at 15 centimeter there. It's all the masses will be at 15 centimeter from that direction. And now I will adjust the pivot position until I get a balance. The horizontal, the meter rule balances horizontally at different masses. So the first is I'll start with the 20 gram mass. So I'm going to start with the 20 gram mass and see what will happen with that distance. This is it here, and that is. So I still have my loop. The hanger and all of this is 20 gram. So I'm going to fix it. It is balanced. This is the so it was at 50. It's already at 50. Horizontally it's balanced there. Now I want to fix this mass. I'm taking 20 gram mass first of all. That's 20 gram mass. I started on the loop. And I want to fix it at 15 centimeter. And that 15 centimeter is there. So I'll fix it right here at 15 centimeter. 15 centimeter is somewhere here. So I ensure it is there. But once I fix it at 15 centimeter, now this width is now larger than the other loop here. So what will happen is it will not maintain horizontal equilibrium, except I now do I now reverse, or I now try to adjust the position of the pivot until there is going to be a horizontal equilibrium here, or a balance point. So let's check this. This is at 15 centimeter there, and that is 20. So now I'm moving it from the 50 and try to balance this 20 gram mass and measure the point where it is going to be balanced. So watch out there. This is This is it. We have yes, you just take your time a little bit so that don't be in haste. This is an experiment that you have to be patient with so that you can get the correct reading. So now it's balanced at that point. It's horizontally balanced. So now I want to get my readings. Watch out for this. This is at 15. Now it has the point where it is balanced now is around 44 centimeter. So it is at 44 centimeter. This is 15. So I want to find that distance from the mass, where the mass is hanging, to where it became balanced. That is the pivot position. Now it is the 44 centimeter. So I'm coming to find that x. So that x is 44 minus. So watch this out. I'm now finding the 44. This is 44 minus 15. You have to be careful. That is 29. This is 29. So I get that. This x is 29.00. So now I put it right here. Now I want to find the y for that. So since it is at 44 and the pivot position was at 50, so now I'm trying to find the distance between this 44 up to 50. So you now know that it's got to be 6 centimeter. So 44. So we can now subtract the 50. How did I get that 6 centimeter? It's because I subtracted 50. You can do that with your calculator. This was the 50 where it was balanced initially. That is the center of mass. And now the new pivot position is this. That's 44. So that's 50 minus 44. That's how I got this 6 over there. So it's 50 minus 44. You can do that. This is how I got a 6 over there. So now that is 6. So y is 600 centimeter. So I've got that. So watch these figures. I'm now going to still fix it at 15 centimeter. Then this time I'm increasing the mass. So I can hold it because this one is going to change anytime I put a mass. Of course, you expect that to happen. So I get it there. Now I'm coming to fix the mass there. I'm increasing the mass. This is another 20. So I add 20 there. This is now 40. So I've taken the 40 from the 40 gram now. So this is now 40 gram. It was 20 initially, I added another 20, so it's now 40. Everything here is 40, and I still maintain this 15 centimeter. I'm maintaining it. Now the weight is increasing, so it cannot balance with this, the mass of the metal roll anymore. So I have to find a new pivot position. So I keep going again. I'm going to now adjust. This is still at 15. I make sure it is still at 15. You have precaution and ensure that there is actually this 15 centimeter is well maintained. So I move. I'm coming to balance it. I balance it until I get the balance point. Now I'm moving it. So there. So now it's balanced at this is the 40 gram mass now added there, and we have seen that it is balanced at a different, the pivot position has changed. It's now at a different pivot position. So here, let me look at it here. It is now at 40 centimeter. It is now at 40 centimeter. So I go back there. This is 40, the 15 minus that 40. Now you can see that it's going to be 25 somewhere here. So watch. This is 25.00, and it's 25.00, and from 40 to 50. It is 40 here, and the center of mass was at 50. So from 40 to 50 is 10 centimeter. So I have 10 centimeters somewhere here. 10 centimeter 00. Right, so I'm moving a little bit. So I come back with the next one. I'm still adding. I want 60 gram now. This was 40. So I'm adding, I keep adding. This is so I've got 60 hanging there. That is 60 that is on that stuff. So I move the pivot. The pivot, it will not balance here because I've added a weight. So the clockwise turning moment cannot be equal to the anti-clockwise. So I have to find a new pivot position where it is going to maintain horizontal equilibrium. So I keep adjusting again until I get a balance point. Here, I get that. You just want to be exact and make sure you do the correct thing. That's why you have to be patient. Just make sure you get the meter rule is actually horizontally balanced before you take your reading. And when you're taking your reading, make sure that you avoid parallax when reading on the meter rule, so that your eye must be vertically on top of the scale, so that you don't read the wrong number. That's one precaution, very important precaution. Now I want to read the balance point. Now it is somewhere around 37.5. It's at 37.5, and this is still at 15. I did not touch the 15. The 15 centimeter is still fixed there. So I've got a new position. It is 37.5. So 37.5, I got that one. So 37.5 minus 15. See, so let's look at it where it is balanced at 37.5, and this is 15. So 15 to 37.5, that is 37.5 minus 15 will give you 22.5. So I just got 22.5 there. How did I get it? It's because I subtracted the 37.5 minus the 15.5, minus the 15. So 37.5 and 15, I got 22.5, like that. So I come back to subtract 37.5 from 50. So you can get it. You can go along with me. You also use your calculator. This is minus 37.5. 37.5. This will give me 12.5. So watch out. This is 12.5. So you can see there's something happening here. Very soon you see the relationship between them as you're moving. So let's proceed again. Now we have got so I'm bringing the last one there, which is another 20 added to this, so that I can have 80. Another 20 added to this is giving me 80. Now I don't expect it to balance because I've increased the weight. So now I'm going to make sure I balance it at a point. You do that. So you saw that I have taken maximum precaution here, so much that the masses are not allowed to touch the table, so that they can actually suspend freely, so that we know the acceleration due to gravity on them is acting on them, so that we don't have any errors on this. So now it's balanced at 35 centimeter exact. It's 35 centimeter, and we are still at the 15 centimeter. So from the x value here is going to be 35 minus 15. So I have 20. So I have 20 somewhere here. This is 35. This is 35 minus 15. Give me 20. This distance is the x I'm trying to figure out. Now I have, this is balancing at 35. So from 35 to 50 is 50 minus 35. Give me, so you see the difference between 50, 35 will give me 15. So again, that stuff, this is 15, 0, 0. So I have already got the readings for all the set of masses 2020. Those masses can vary. It could be if I had maybe some of the time I would try to do it for the 10 grams, so you see what happens. I can also vary them, but I just wanted to use the 20 grams. So these masses can also vary. The same result is bound. So now let's check this out. Now we want to plot a graph of x and m. Then we'll also plot a graph of y and m. Yeah. So all of this, I think you can do all by yourselves. Now you want to see the relationship, but let's see what happened here. You found out that as I was increasing the mass, the mass was increasing, and this distance x was becoming smaller, was coming down. You see, it was dropping actually. So there was an inverse proportionality between the mass and x. As I was increasing the masses, the distance between the suspended mass and the pivot, the new pivot position, was reducing in this order. You see, increase and reduction here. The reverse was happening here. As I was increasing the mass, what was happening within this distance between the center of mass and the new pivot position, that y was increasing. So as x was reducing, that's how y was increasing. So you can now use your own graph paper and you try to plot this. But I've just given you a relationship between them. You can see that there is inverse proportionality between the m is increasing and x is reducing. That's inverse proportionality. And there is direct proportionality between y and m. So as m was increasing, y was also increasing. That's what we have just investigated. So we have tried to show the relationship between this distance and the force with respect to this fixed distance. So you can repeat this over and over and you can get the same result approximately. So we are going to pause here for now and we continue some other experiment. It's also possible that I can now fix, this one was fixed, I can fix this and try to get a counterweight such that this weight will balance. I want to know what weight will balance exactly this. So let's see now I have my 80 gram mass here and I have the 15. So I'm going to fix another mass. Now let's see, I want to know at what pivot position will this is 10, 10, 10, this is 30 gram mass. When I suspend it on the reverse side, yeah, I'm done with the first experiments. I'm just trying to now give you a couple of extended experiments on stuff like this. So now I also want to find what's going to be the point where the two of them will balance. So now I have a mass here. So I want to investigate something. Now this is at 15. I fixed it at 15. Now I want to see if I can put this rule at 50 centimeter and this is 45, 50 centimeter. Now I want to see if I fix that at 15 centimeter and I want to know what point will make this mass balance. Now I have to reduce some of the masses here so that I get so just wait for me a little bit. Let me just check something here. I just reduce some of these masses and so that we get another. So I reduce it a little bit. So hold on. Now we have this. I've got it there. Now I have reduced the masses here. So this is still at 50. 50, that is the center of mass of that stuff. So I just fix this at the same 15 centimeter mark. I fixed, now it is of 40 gram. This is 220s, this is 40 gram. Now I have brought in another 30 grams somewhere here. I want to see at what point will this balance. So you can see what I'm coming to do here. So check out, see what is happening here. We have, now I can put it 2. Now you see that it is balanced with this. So this clockwise turning moment was equal to the anti-clockwise turning moment. And it may be asked to find this distance. I want to investigate this distance. So it's 50, it is balancing at 87. 87, so at 87 we have the rule balances at 87. 87 to 50. Now we can investigate this distance. We found out that it was at 87 centimeter, that is 50 to 87. So you can fix if you want to draw that, you can add something like this. So we have, this is the 30 gram, and I have my 40 grams somewhere here at the 15, and this was at 50 centimeter. Now it has balanced at the 80, this was at 87 centimeter there. So this was at 0. So now 15 to there, you can still investigate this. This is 35 centimeter. Now I can now find this distance x. I can vary this distance, and that is this is another relationship I can find. What if the masses are on either side? Then I can find where the balances are going to vary. So in that case, I will fix one constant. Let's say I'm fixing this constant, then I'll vary that. So either ways you can do it. You can fix one of the masses constant and you keep improving on the amount of masses there, and you still use your you adjust the loop to get the balance point. So this X keep varying. So if I wanted to like change the same thing here, so I can fix this as a permanent place, and I don't change this, but I can now be changing these masses and find the length, the distance between the pivot, the balance point, and this. It's also possible that I can do that, but for this experiment, we want to like just find the distance between them. Where is this mass going to vary, to balance from the pivot to here? So this can be also investigated. In some other day, we can investigate this. We want to fix this constant, and we put the pivot constant. There are two constant positions I'm maintaining here. I'll fix this mass here constantly, then I fix the pivot position constantly, then I now try to vary the position. I adjust this loop for different masses. I can put a 10 gram mass, then I adjust such that it will balance at a point, then I measure this distance here. So that X will change as I'm moving. Then when I'm done, I add the mass also. I fix this 15 centimeter, this mass at 40, I fix it at the 15 centimeter. I'm just using 15. I can fix it to any number, 10, whatever. So now I fix this. I also fix this at the 50 centimeter mark. That is the balance point. That is the center of mass. I keep it there. Then I will come and adjust, meaning I change this mass. When I change the mass by increasing it, of course when I increase it, there's going to be an imbalance. So I have to adjust the distance such that there is a balance. The meter rule balances horizontally, and I'll now measure this distance. So this X keeps changing as I'm changing the masses. If this was the 40, this is kept constant, and this position is also kept constant, but I keep changing this. I can put a 10 gram mass, then I adjust it. I'll try to read this distance. Then when I'm done, I add another one. This is plus another 10. I add the same mass, so I still keep this constant at 50, keep this constant at 15, then I adjust this other one so that I get this of course this X will be changing as the mass is changing, because for it to balance it's going to be different there. So that's it. Now you can do this experiment some other day, but I just wanted to see a relationship between them. So as I'm changing the mass, you can see that the distance here is also going to change when I keep this constant. It's also possible that I can keep this constant, then I keep this constant, then I adjust the pivots such that I have the balance points as possible. That's another option I can do here. I can keep this at a particular number, like say 90. I keep this at another number, let's say 10. Then I try to adjust the position of the pivot such that I can have a balance. When it is balanced horizontally, then I can measure this distance and measure this distance and get the relationship between them. It's possible that I can be increasing the mass concurrently. I can increase here, likewise here. I'll be adding here, then I try to get a balance point, then I'll read this point and read this distance. It's possible that I can do. There are a lot of investigations you can do here, but just understand that for this our first experiment, there was a relationship between them. This one is just an extension that I was trying to do, that with this experiment we can do further investigations. We wanted to know if I put the two masses on either side of the pivot, what happened to this distance? That's an investigation we wanted to do. But I can also fix this, and now to vary these masses and try to adjust it so that there is a balanced position. That point where it is going to balance, I'll read that point and try to get this distance there. That is what I'll do, and I will do it for several masses. Whilst keeping this constant, I can change these masses also. Then I try to balance the point, find the balance point and measure this distance as possible. This is another form of this experiment which I can do. But we'll keep this for some other day. I'll bring this later on. So let's just pause here whilst we go to another thing. So thank you for your audience, and I want you to keep following by trying to subscribe and also try to follow up the lessons as we go. It's a series of lessons I'm bringing out. You may want to follow up so that when I put in a new stuff, you'll be able to see. So try to subscribe and we move together. Thank you for your audience and keep watching. Let's go.